All right, so moving on to diesel power cycle. So it says diesel gas power cycle. The gas refers to the fact that it's a gas power cycle. So the working fluid stays in a gas phase, not to be confused with gasoline. So the actual cycle is a little bit different from the gasoline cycle. So let's look at a gasoline engine real quick. So and we went over it already, but with a gasoline engine, what comes into that intake valve during that first that intake stroke is air and fuel. And so what you're compressing are air and fuel, and you compress it to a high enough temperature and pressure um, over over here, high enough temperature and pressure such that once that spark plug sparks, right? Once you have that initiation of that combustion event, what's it, you're not injecting any fuel or anything. You've compressed this very highly combustible air fuel mixture, and the initiation of that combustion product is your spark or the I'm sorry, the initiation of that combustion event is the spark plug. That is different from what's going on with your diesel engine. So what you're compressing, what's coming in is just air. What you're compressing is just air, not air and fuel. And what initiates that combustion process is the compression of that air above the auto ignition temperature of the fuel that's being injected. And so when it is injected, now it's injected into an environment that's above the temperature of its auto ignition temperature, and that's what initiates that combustion process. And then the rest of it is the same, right? The products of you've got the power stroke, and then you've got the exhaust stroke where your products of combustion leave that piston cylinder. Um, so again, we have the diesel cycle, which is modeling the diesel engine and the diesel, which is not really a thermodynamic process, right? You're not just working with air. You don't have a closed system. You have fresh air coming in and combustion products going out, right? You don't have this closed system where you've got air undergoing lots of processes, right? Four processes, and then state one to state two, state two to state three to state four back to state one, and then the same air undergoes the same process over again. It's not really what's happening, but that's our very simplified model to what's happening. All right, so once again, our model, we're treating it like it's a closed system, treating it ideal air standard assumptions, right? Or ideal cycle assumptions, air standard assumptions. Airs are working fluid, closed system, exhaust products and exhaust and combustion processes are replaced with heat rejection and heat addition processes. We're going to ignore kinetic and potential energy changes, and our four processes in this very, very simplified model are from 1 to 2, you have an isentropic compression process. Looks very similar to the Otto cycle. And I'm going to skip 2 to 3 right now. Let's move on to step 4. Step 3 to 4 is an isentropic expansion process. Looks really, really similar to that Otto cycle. Man, if you've memorized it for the Otto cycle, now you got it for the diesel cycle as well. And for the last one, it's a constant volume heat rejection process. Looks very similar to the Otto cycle, and it is. And when you apply your first law, it's going to look exactly the same as for that Otto cycle, right? Your work for the compression process is going to be work in. Your work in is going to be U2 minus U1. For the expansion process, your work out, it's going to be 3 minus U4, right? Go through, apply your first law, figure out, is it delta U or is it negative delta U? Your constant volume heat rejection process, your Q out. This is going to be 4 minus U1, all the same as the Otto cycle. The only difference in the way that we're modeling it is that process from 2 to 3, the way that we model that combustion process. With an Otto cycle, you modeled it with a constant volume process. Here we're going to model it as a constant pressure heat addition process. And so if I apply my first law, let's see what I've got. And make a note for the heat addition process. Actually, let's just look at our first law here. So we have a constant pressure heat addition process. That means I don't have a Q out. I have a Q in. Great. Perfect. But this is not a constant volume process. The work is not zero here. And so when you add that heat, you actually have some expansion of your working fluid. So you have a positive boundary work. You have work out, work generated. And so you have, I'm going to put it in lowercase letters, you have a Qn minus, you'll have a work out. So you'll notice that for this cycle, you actually have two workouts and one work in. So when you calculate work net out, you're going to have this, you're going to have this workout plus this workout minus this work in, and that will be your work net out. Okay, but going back to process 2 to 3, you applied your first law. It's Q in minus Q out equals delta U. Delta U would be, U3 minus U2. Okay, perfect. Well, make a note, this workout, it's boundary work, right? And this is on your equation sheet with the boundary work, there we go. Yeah, there we go. You've got a expression for boundary work. Yes, quasi-equilibrium. I'm probably not going to write that. Quasi-equilibrium is kind of a fancy word for reversible. So yeah, by making these assumptions of air standard assumptions, that's kind of implied. So long story short, if you're having to calculate boundary work, it's integral PdV. Okay. Now the equation on your equation sheet is in terms of capital letters, so I'm going to divide through by mass and put it in terms of little w and specific volume. So this is going to be the integral P dV. And because it's a constant pressure process, that pressure is going to come out of the integral, and it's just going to be P delta V. And now what I'm going to do is I'm going to bring, let's kind of have this over here. I'm going to bring that little workout term over there. All right, and so now this is going to be delta U plus, that's P delta V. And this right here is just the expression for delta H, which would be H3 minus H2. So one small difference, make sure that you understand why it's delta H as opposed to delta U. Make sure you got that, right? It's important to know why, right? There's power in knowing why. Don't just memorize, know why, right? But it's easier in the long run. All right, so we are going to go over a problem in just a second, but there are additional diesel problems that you can solve, or the additional videos for diesel problems if you want to solve those. All right, so let's move on to problem 3. All right, so problem 3 is an ideal diesel cycle. We have a compression ratio of 18 and we have a cutoff ratio of 2. Oh, no, what's the cutoff ratio? Forgot to talk about that. So our cutoff ratio, it's V3 over V2. And remember we had from 2 to 3 of this constant pressure heat addition process. So you've got this expansion, and that cutoff ratio is what captures how much it expanded. It's the ratio of the volume after that heat addition process versus before. Okay. All right, we've got the initial temperature, pressure, volume. It's in English units, but what are you going to do? And then we want to find the net workout, and then we also want to find the mean effective pressure. So again, you will not be given all the stuff that's in black. The only things that you would be given are the stuff above this squiggly line here on a test. So make sure that when you go back and study, cover up everything that's below that squiggly little line there and make sure that you can understand what that problem statement is telling you. All right, so again, let's start off. This is a different squiggly line. So everything above that line up there, that's what you need to, that's what you would be given on a test. All right, so let's go ahead and start by getting our governing equations. Oh, and also, They did tell us to solve the problem using cold air standard assumptions. And there is a problem on the YouTube Unit 1 playlist that has the same problem solved with air standard assumptions. So make sure that you are comfortable doing that. But this one, we're just going to do cold air standard assumptions just to kind of move through the problems a little bit easier. Okay, so yeah, changes in kinetic and potential energy are negligible. Those are our assumptions. Steady state, cold air standard assumptions, which means that it's an ideal gas. We don't have heat transfer where it's unintended. No irreversibilities. Yeah, that got all the air standard assumptions, which we just kind of listed all three of them. And then we've got the CP and the CV, and this is taken at 300 Kelvin. All right. So again, you can look these values up in A20E at, well, 300 Kelvin, 540, 500 was 77 degrees Fahrenheit, 540 degrees Rankine. Okay, so let's go ahead and get our governing equation. So the work net out. Work, I'm going to write it in green. What's that work net out? All right, so I can put it in terms of all the work out minus all the work in. Keep in mind, I don't know why this doesn't have a 2 to 3. Keep in mind, you have work in here, you have a work out here, but you also have a work out here. So the work from 1 to 2 and 3 to 4, those are in terms of delta U's. The work from 2 to 3 is in terms of P delta V's. And if you don't have to calculate those specific volumes, the delta V part, why add extra work on yourself? So what I like to do is I like to, for any cycle, your work net out is equal to your Q net in. Q net in being any work in or any Q in minus any Q out. That's for any cycle. And if you want to see why that is, watch on the Thermo 1 playlist, review for yourself. Just, I think it's probably the first, it's on Unit 4. It's the Unit 4, probably the first video, cycles. That's it, thermodynamic cycles. Okay, you're applying the first law to a cycle. All right, so this is equal to your Q net in, which is any Qn, and we only have got, or you got a Qn, you got a Q out. So any Qn, write it as red, minus any Q out. I'll keep it as, kind of want to put it as blue, but I'll just keep with red. Any Qn minus any Q out. Now we do have capital letters here, so I'll put this as M. And now this is Qn minus Q out. All right. And now I need to put those Q ins and Q outs in terms of delta U's, or in the case of the Q in from 2 to 3, it's going to be in terms of delta H's, isn't it? But before we get there, let's do our mass, because we're not given mass. However, we are given enough information to calculate that mass because we've got the initial temperature, pressure, and volume. Because MRT equals PV. Or this is R bar over molar mass. That's your universal gas constant, R bar. And your specific gas constant, R without the bar, is going to be that the specific gas constant without the bar is in terms of, well, it's going to be in terms of mass. So in English units, this would be in BTU per pound mass degree Rankine. Yeah. But your R bar would be in terms of BTU per pound mole degree Rankine. So we do need to kind of keep that in mind. So that's fine. All right. So this is going to be, it's going to be PV P over R bar over molar mass T. So this is going to be R bar T, and then there's going to be a molar mass up here. And of course, I'm looking at state 1, so might as well put that there. And then, of course, I've got things in terms of delta U's and delta H's. So Qn is, on your previous page, it's H3 minus H2. I don't expect you to memorize, is it H3 minus H2? You need to be able to write that first law down, figure it out, right? Because we're going to analyze so many cycles in here. If you start trying to depend on memorization alone, you're going to get screwed. And even more so if I switch numberings around, right? Q out is from 4 to 1. This is, I don't know why I'm color coding it now, but this is U4 minus U1. But keep in mind, cold air standard assumptions. That's fantastic. So that delta H is CV delta or CP delta T. The delta U is CV delta T. So yeah, let's go ahead. I think I want to make sure that I can get this in terms of pound mass. So let's just make sure. So I've got my pressure. So it's a little bit smaller. So I've got 14 pound force per inch squared times the volume, 117 inches cubed, molar mass for air. This is found in table A1E, and it should be 28.97 pound mass per pound. Your R bar is at the bottom. I'll show you right now. Yeah, right there. So it's on page 5 of that heat transfer packet. It's at the bottom of the conversion factor sheet. And so you've got, got two forms of that R bar in English units. I'm going to use the bottom one, 1.9, I think, anyway. Actually, it really doesn't matter. I think actually I'm going to use this one right here because I know I'm going to have with that pounds force per inch squared, right? The PSI, I've got a pound force in there. So I'll use 15.5. So 1545. This is foot, pound, force per pound mole, degree Rankine. And then I've got a temperature as well. So my temperature is initially 80 degrees, so 80 plus 460. And that would give me degrees Rankine. All right, so let's just see what I've got. So I've got inches squared, that's just inches, pound mole, degrees Rankine, pound force. You have a pound mass as long as you deal with the feet. So yeah, 12 inches per 1 foot. Yeah, inches, feet. Perfect. So you should get something. Oh, sweet Lord. Don't know. Have it somewhere. One would have thought. Well, somewhere I've got it. Those are the numbers that you plug it in. But that's going to be in pound mass. Okay. So what I'm going to do, I think I'll kind of highlight that part. Right, that's what's going in this little section right there. That's that right there. Okay, fine. And then so that's mass. whatever I calculated right there. And then it's going to be CP delta T. So CP T3 minus T2 minus CV delta T. CV T4 minus T1. Perfect. Perfect. Alrighty. So I've got my CP and CV. Those are found in table A20E at 300 Kelvin. And now I just need to plug in those temperatures. So I do need the temperatures, don't I? That would be important. All right, so state 1, T1, 80 plus 460, it's Rankine, 540, it's Rankine. Actually, 537. I think I was saying 540 before was equivalent to 300 Kelvin or 77 degrees Fahrenheit. It's 537. I'm sorry. Yeah, 537. Right, now we need state 2. So I know state 1 to state 2, we have a constant pressure heat addition process. I'm sorry, no, State 1 to state 2 is an isentropic compression process. So it can apply an isentropic relationship. So isentropic relationship between 1 and 2, because I have an isentropic process. And I'm assuming specific heats are constant. So it's going to be 2 over T1 is 1 over V2 to the K minus 1. Remember, you're using the isentropic relationships that are for constant specific heats, right? So those easier equations. Make sure you put it in degrees Rankine, otherwise it ain't gonna work out. That V1 over V2 is just R, so this is R to the K minus 1. And so I've got a T2 of 1716 degrees Rankine. So yeah, I'm going to kind of put like some happy little purple clouds around the temperatures that I'm going to need those governing equations up there. State. All right, so state 3. Well, I know that from 2 to 3, I do not have an isentropic process, right? This is a constant pressure heat addition process, so it is not an isentropic process, so I cannot use an isentropic relationship. But I can always use either my first law or I can use my ideal gas law, and I think probably my ideal gas law is going to help me. Let's see why. So between 2 and 3, I know that MRT3 over P3 V3, I know that this is equal to MRT2 to V2. Why? Because they're each equal to 1, so they're equal to one another, right? And so now I can cancel out some stuff, right? Modeling it as a closed system. Specific gas constant is constant. From 2 to 3, we have a constant pressure heat addition process, constant pressure. And so now you see that T3 is going to be equal to T2 times V3 over V2. And I can also put that in terms of specific volumes. It doesn't really matter because the ratio of those volumes and the ratio of those specific volumes is just cutoff ratio, isn't it? And that's given to you, that was 2? Yeah, cutoff ratio of 2. So T3 ends up being something 3432 I'm sorry, 34.32 or 3432 degrees Rankine. Perfect. So I'll put a happy little bubble around that. That's good. Now I got state 4. So state 4, you've got from 3 to 4, you do have an isentropic expansion process. So remember, 3 to 4 isentropic expansion process. So you can do an isentropic relationship, right? So T4 over T3 is equal to V3 over V2. I'm sorry, 3, 4 to the K minus 1. And I might have a little bit of a problem here because I know V1 over V2, I know V2 over V3, right? That's the compression ratio, the cutoff ratio, but don't know V3 over V4. However, what I am going to do is I'm going to kind of manipulate this a little bit. So V3, I know V4 and V1 are equal to one another because from 4 to 1, you've got a constant volume heat rejection process. So this is equal to 1. And then I also know I'm going to kind of change this around. Let's put this as V3 over V2 times V2 over V1. I have not changed anything, right? It's still going to be equal to V3 over V1 and ultimately V3 over V4. But now I have things in terms of the cutoff ratio and the compression ratio. And so now I can calculate what my T4 is, and my T4 ends up being 1425 degrees Rankine. So I'll put a little bubble over there. And going back to my governing equation for my work net out, I do have a number for that. So my work net out is 1.24. 1.24, and it's BTU. Do you watch your units there? Make sure that you could see how the units work out the way that they do. We also needed to figure out the mean effective pressure, and I guess I didn't really get into governing equation for that, but that's okay. We'll do it now. So my mean effective pressure it's equal to my work net out, which we calculated already, although we calculated it from Q net in, over our Vmax minus Vmin. Well, your maximum volume is before the compression. Your minimum volume is after. And again, I could put it in terms of mass times specific volume, but it doesn't really matter. It's V1, and this would be 1 minus V2 over V1, which is 1 over R. And I end up getting, watch your units. Again, make sure that you can see how the units work out. Go through, cross them out. Our mean effective pressure ends up being 104.7 PSI. Right, so you've got BTU on the top and you'll have inches cubed on the bottom. So make sure, figure out how BTU per inches cubed ends up being pound force per square inch. Okay. All right, and that's it. All right, so I guess there's nothing else to do except go on to gas turbines. All right, so gas turbines. So if you haven't watched video 1.7, go ahead because I'm going to go over this very quickly. So an actual gas turbine engine looks like this. We are going to model it. Well, this is really like the simple process, and this is the actual process. You've got a compression process. You've got air coming in. Then that air is compressed to a higher pressure and temperature, goes into a combustion chamber, add fuel, combustion happens, and then that very high temperature, high pressure, high energy working fluid is expanded through the turbine. You get work out of it, and then you get your products of combustion going out to the atmosphere. All right, the very simplified model that we're going to use is the Brayton cycle. Now, one thing you'll notice, this is not a piston cylinder arrangement. So you have compressor, you've got turbine. We're going to have heat exchangers that we're going to use to model the exhaust and combustion processes. These are all, if analyzed on their own, they are all open systems. So just be aware that you're going to now have to use the first law for an open system. We analyze each of these devices. All right, so our ideal model, just using air, just modeling it as if we have air. We're not worrying about fuel or anything like that. We're modeling the heat are the combustion processes as heat addition processes, and the combustion processes as heat rejection processes. So 1 to 2, you get an isentropic compression within that compressor. From 2 to 3, again, we're modeling that combustion process as a simple heat addition process, and we're we're modeling this such that there is no fluid friction, which would cause a pressure drop across that heat exchanger. So anytime when we talk about cycles in this class, you see a heat exchanger, we're not considering that there is any fluid friction, again, causing a pressure drop across that heat exchanger. Then from 3 to 4, expansion through the turbine, and then from 4 back to 1. Notice that that heat exchanger at the very bottom is drawn with little dotted lines, and that just indicates that this is not a real physical component, but it is a model of how we're modeling that exhaust process. We're modeling it as if there were a heat exchanger there and it was a constant pressure heat rejection process. But again, there is no heat exchanger there. It's an imaginary one. We also define what's called the pressure ratio. So instead of having things in terms of specific volumes, as it is with the compression ratio in a piston cylinder arrangement for the Otto and the diesel cycle, now we have a pressure ratio, P2 over P1. Notice that that compressor and the turbine are physically connected, and we can define another parameter, which is the backwork ratio. So it's the work of the compressor over the work of the turbine. And it is used to describe the fact that a portion of the work that turbine produces is used to drive the compressor. Okay, so I guess that's about it. Let's go ahead and move on to problem 4. All right, problem 4, we have a simple Brayton cycle. We've got a pressure ratio of 8. So I went ahead and drawn out the simple Brayton cycle. With a simple Brayton cycle like this, I would expect you to be able to draw it yourself, but when we start adding stages of intercooling or reheat, as we'll see, or regeneration, then I will probably give you that diagram. But if it were a simple Brayton cycle like this, I probably wouldn't necessarily give you that diagram. It would be up to you, just like it would be up to you to memorize the processes for an Otto cycle and a diesel cycle, memorize it for a simple Brayton cycle. Okay, also make sure that you know that this diagram right here has absolutely nothing to do with an Otto cycle or a diesel cycle. An Otto cycle and a diesel cycle are piston cylinder arrangements. There is no turbine in your car. There is no, right, that it's not, that there's none of that in your car. And so I see it so often that I have to point out, please don't draw turbines and when you're talking about Otto cycle and diesel cycles. Okay, it sounds silly when I say it, but I see it often enough that I have to point it out. Okay, so I went ahead and drawn on there what the pressure ratio is. They also tell us what the temperatures are going into the compressor and into the turbine, but they also tell us those isentropic efficiencies for the compressor and the turbine. So I've drawn those on there as well. Now, before I do anything else, let me go ahead and make a note of where my Q ins and my Q outs are, because I will say this, even on more complicated diagrams for, if I have a Brayton cycle, but it's not a simple Brayton cycle and it's getting a little bit more complicated, I'm not going to tell you where Q ins and Q outs are happening. That's up to you. So for a compressor, this is a work in. For a turbine, this is a work out. Okay, so this is a work out. This is a work in. Yeah. So from 1 to 2, you've got a, well, here it's a non-isentropic compression process. And then up here, you've got your constant pressure Q in. Down here, you've got your constant pressure Q out. There we go. So I've drawn all those things. Let's go ahead and get what are we supposed to find? We are supposed to find the backwork ratio and then the thermal efficiency. So up here, it does say, if you want to solve it using air standard assumptions, go ahead and watch this video. So I am going to also defer to you to watch that video, and let's just spend the time that we have right now going through how we would solve it using cold air standard assumptions. So cold air standard assumptions. All you're going to need are temperatures, okay? So the nice thing about cold air standard assumptions, you will not need to look in those ideal air tables at all for your properties. Perfect. So let's go ahead and get our governing equations. Also, what I'm going to do here, I am going to go ahead and just write my first law for an open system. dE dt is equal to Q dot in minus Q dot out minus W dot out is W dot in plus the sum of the M dot H's. And there are kinetic and potential energy changes, but I'm going to go ahead and ignore those. So it's just going to be M dot H going in minus M dot H going out. I'll put I and E. Okay, perfect. We're also assuming it's steady state, so I guess I should get rid of that as well. Okay, perfect. So everything's going to be in terms of delta H's, nothing in terms of delta U's. So when you define your governing equation, and I'm actually going to write it on the air standard assumption side, and then I'll extend it to the cold air standard assumption side. The back work ratio is the work of the compressor. So work of the compressor, which is the work in, so it's the work in over the work out. All right. So again, referencing this thing up here. So I know I've got things in terms of W dots and Q dots and everything, but notice that if I just look at, let's look at the W dot in. If I draw my control volume just around this guy right here, it's a one inlet, one outlet system, steady state. So the M dot's going to be the same. I will not have, I'm going to go ahead and cancel stuff out. I don't have a workout. I don't have any Q in or Q out. That isentropic efficiency being less than 100% references the irreversibility portion of it. So this is going to be, I'll have W dot in is equal to the sum of the M dot H's going in minus out. And if I divide through by M dot, I'm just going to get H1, actually H2, right? Got it? Yeah, H2, I'm sorry. H2 minus H1. Go over here, do the same thing. Apply my first law to my turbine. I'm not going to have a W dot in. I'm going to have a W dot out. And so it's just going to be in terms of H3 and H4. This will be H3 minus H4. H3 minus H4. I think this needs to be a little bit smaller. There we go. H3 minus H4. And it's the exact same thing over here if I make cold air standard assumptions, except now that back work ratio, I can put this in terms of Cp delta T. So Cp T2 minus T1 over Cp times T3 minus T4. Perfect. Of course, those CPs are going to cancel out, but there you go. So I'm going to go ahead, I'll highlight this. This is my governing equation for the back work ratio. So I'm all good there. Color it all in, otherwise it's going to annoy me. All right, now I've got the thermal efficiency. All right, so again, thermal efficiency. Let's do it on the left-hand side, and then we'll extend it to the right-hand side. So thermal efficiency, it's work net out over Q in, or 1 minus Q out over Q in. So let's go with the 1 minus Q out over Q in. Doesn't really matter. I will say a good thing to do is calculate it both ways and make sure that you get the same value, because if you didn't, you probably messed up one of your H's somewhere. All right, so your Q out happens between 4 and 1. If you've watched the video on the simple Brayton cycle and the derivation of those equations, I'm going to assume that you have. Then when you apply your first law up here and you cancel out, well, for your Q out, you're going to have lots of things cancel out. And so you're going to have things just in terms of delta H's. This is going to be H4 minus H1. Make sure you watch the video if you haven't. Make sure you do, and make sure that you understand why it's H4 minus H1 and not H1 minus H4. And then the Qn is between 2 and 3. This becomes H3 minus H2. Again, if you do cold air standard assumptions now, this becomes, you could put this in terms of 1 minus Cp delta T. So T4 minus T1 on the top, and Cp T3 minus T2 on the bottom. And of course, those CPs are going to cancel out. So you can see the only thing that I'm going to need, are the temperatures. So there we go. It's okay. Okay, perfect. All right, so let's go get our temperatures. I know T1 and T3, so I'm halfway there, aren't I? All right, so from 1 to 2, you've got, it would be an ideally isentropic expansion process or compression process. And this is the point where I say, if you don't remember anything about isentropic efficiencies, go back to the Thermo 1 playlist. It's Unit 6. Watch the video on isentropic efficiencies. Okay, so I need, so state 2. Actually, I'm over here. So state 2. All right. So you've got this you've got an isentropic efficiency that is less than 1. So I'm actually going to need to calculate two T values. I need T2S, which is the temperature at the end of an isentropic process, and then T2, which is what it actually is. So T2S is if it truly was an ideally isentropic compression process, in which case I could use an isentropic relationship from 1 to 2, because again, ideally it would be an isentropic process. So go into my equation sheet. You've got a couple of isentropic relationships. I'm looking on the left-hand side because I am assuming that the specific heats are constant. Now, when we had Otto and diesel cycles, we used this guy right there because we happened to know the compression ratio, and so we knew V1 over V2. But here in the Brayton cycle, we've got pressure ratios, so that's the one that we're going to use. So T2 over T1 equals P2 over P1 to the K minus 1 over K. It doesn't say T2S. That is implied because it's an isentropic process. Okay, isentropic relationship. Okay, so this guy over here. So I've got T2S over T1 equals P2 over P1 to the K minus 1 over K. That K is 1.4. P2 over P1 is 8. T1 is 300 Kelvin. They were really nice. They gave you what that was. Your T2S ends up being 540. Oh my goodness, I can't. Too small. 543.4. 543.4 Kelvin. That is not the value you're going to plug into that into your governing equation. You need to find state 2. So state 2 is found by using your isentropic relationship, or isentropic efficiency, I'm sorry, which relates the isentropic and the non-isentropic process, the isentropic and the real world process. So, all right, so isentropic is on the top, regular is on the bottom, right? Ideally, you want the smaller number on the top, right? Ideally, you wouldn't have to put a lot of work into this compression process. That's a smaller number. But in reality, because of irreversibilities that you got to deal with, you're going to have to put in more. So this guy, you've already defined him. This is the work input. It's Cp delta T, T2S minus T1. This is Cp T2 minus T1. Of course, your Cp's are canceling out. Calculate what your T2 is. Right, so your T2 ends up being 604.25 Kelvin. And whoops, and that That is the number that you're plugging in. All right, one more temperature to solve for. So state 4. So state 4 is right after that non-isentropic expansion process in your turbine where you're getting your power output. So this is going to be, you need to find a 4S, of course. And so again, you're going to apply an isentropic relationship between states 3 and 4 because ideally it would be an isentropic process. So this is not T2S over T1, it's T4S over T3 equals P4 over P3 to the K minus 1 over K. Do we know that? I don't know. Let's go see about those pressure ratios. So I've kind of jumped the gun over here, right? When you've got in this class, the only assume that that cycle is following air standard assumptions or cold air standard assumptions, except where indicated. So the places that they indicate that you have irreversibilities is within the compressor and the turbine because you have isentropic efficiencies that are less than 1. But everywhere else, go ahead and assume that there are no irreversibilities, which means that from 2 to 3, you don't have any fluid friction causing a pressure drop. So P2 and P3 are equal to one another. Same thing between 4 and 1. So now you know that the pressure ratio between 3 and 4 is just the inverse of what it is from 1 to 2, right? It's 1 over 8, right? So P4 over P3, 1 over 8 to the K minus 1 over K, K being 1.4. So I have a T4S value of 718. Again, that's not the value that I'm going to use in my governing equation. I need to use my isentropic efficiency for that turbine, which is 0.85 to relate the two. Now in this case, it's not WS over W, it's W over WS. It's the work output for that turbine for the actual process over the work output for the ideally isentropic process, because ideally you get a lot of work out of that process, right? That's the one on the bottom, but in reality, because of your reversibilities, you're going to get a little less. All right, and so you've already defined that work out. This is going to be a CP delta T. It's T3 minus T4 over CP T3 minus T4S. And so I get a T4 value of 804.3. That is the value that I'm going to plug into my governing equations up there. And so I'm all good here. I mean, at this point, as long as, there's clearly no unit conversions or anything to do. And so it really is just plug and chug. I actually do not have a value, but honestly, if you've got this much information on a test, that's going to be good for me. As long as it's completely obvious what I'm plugging in, I'm good. So, I mean, as far as grading purposes goes, it's much better if you get a number. It's easier. But there's only 16 of you, I think, at last check. So I'm not too worried about it. So, okay. Oh, look at that. I gave myself like so much room and then I didn't realize it. Oh well. All right, so I think it's time to move on to regeneration. All right, so what are we talking about? Regeneration. So if you have not watched the video on regeneration that walks through this a little bit more more slowly, do make sure that you do, because the point of this is just a real quick recap of what's important. So talking about increasing thermal efficiency. So that's the name of the game, right? Increasing the thermal efficiency of your cycle. So if I look at the thermal efficiency, there are a couple of terms that I can mess with. I've got the work net out term that I can mess with. I can also work with that QN. So if I minimize the QN, I'm going to decrease the amount of work that if I decrease the QN, I'm going to increase the thermal efficiency of my cycle. So regeneration is how we decrease that QN. which ultimately leads to increase in the thermal efficiency. So this first little panel is showing a simple Brayton cycle, okay? And so one way that we can decrease that QN is by preheating the air before we go into that combustion chamber, right where you see at state 2 in this frame. But yeah, so the way that we do that is with regeneration. So you could see we've stuck an extra an extra heat exchanger there. So the regenerator kind of connects the piping between 5 and 6 to the piping between 2 and 3. So coming out at state 5 out of that turbine, we've extracted a lot of energy in the form of usable work, but there is still a lot of energy in that working fluid. And so the regenerator kind of recaptures some of that energy that would have been lost, right? Because keep in mind, this guy right here, he doesn't really exist, right? This is how we're modeling the exhaust process. And so same over here, he doesn't really exist. And so in our simple Brayton cycle, you can see a highlight the working fluid that's coming out right here. Well, all the energy that's associated with that, it's being thrown out with the exhaust, right? And so we want to capture some of that and redirect it back into our cycle. Some of it's still going to be lost because that's part of the second law of thermodynamics. You're going to have some Q out. But we could still capture some of it and not waste that energy. So we transfer some of that energy back into our cycle before it's rejected to the atmosphere. All right, and how do we define how well it's doing that? Define a regenerator effectiveness. So we could define that using the bottom squiggly or the top squiggly, okay? So the regenerator effectiveness, it's Q regen over Q regen max. So let's define it for the bottom squiggly. So Q regen, it's going into that bottom squiggly. So if I apply my first law to that little bottom squiggly, I'm going to get things in terms of delta H. It's going to be H3 minus H2. And the Q regen max, the one on the bottom, that's going to be the case if by the time my working fluid flows from state 2 to state 3, it's heated all the way up, because that's what's happening. We're adding heat, right? We're adding heat from this part of the cycle, and he's going to be transferred in there. We're adding heat, so he's heating up. The maximum heat that could be transferred, Q regen, would be the case if by the time my working fluid flowed from state 2 to state 3, he has heated all the way up to the same inlet temperature as T5. And in which case he would have the same enthalpy as state 5. Okay, so that's this guy right down here. And so if we have cold air standard assumptions, now this becomes CP T3 minus T2 over CP T5 minus T2. And the same sort of reasoning goes into if we define it from the other side, right? Defining it from the top squiggly, right? Q regen between 5 and 6. If I apply my first law to that top squiggly, I would see that the Q regen coming out of that top squiggly is H5 minus H6. But the maximum heat transferred out of that top squiggly would be if by the time that working fluid flowed from state 5 to state 6, he would have cooled all the way down to state 2, in which case the temperature at T6 and T2 would be the same, and the enthalpy at state 6 and 2 would be exactly the same. So cold air standard, this would be CP T5 minus T6 over, oops, no, he's not working. Oh, there he goes. I'm sorry, I got the little eraser. Over CP times T5 minus T2. So I know that was rather quick. Again, if you want to see it walked through in a little bit more detail, make sure that you go and watch that video on regeneration. All right, let's move on to problem 5. All right, problem 5. We have a cold air standard Brayton cycle. Let me get my stuff all ready here. So again, I've got my diagram here all marked up. Notice that I have not drawn it as a closed loop. That's how we're modeling it because we're modeling it as a cycle. And so, we just want to kind of keep in mind that even though there is not one, are modeling it like there is a magical, invisible heat exchanger when there's really not. And that's where our out is happening. So I'll put this as a Q out. Okay, so even if I gave you this schematic on a test, it's still going to be up to you to figure out what the Q ins and Q outs are. So I note that's a Q out. Over here is my combustion process. This is a Q in. I do have some Q regen happening here. Maybe I'll write that. That's my Q regen. I do have a work in. I also have a workout. Perfect. I think that's it. So I'm supposed to find the back work ratio and the thermal efficiency. So back work ratio, keep in mind, even though it kind of looks like a stretched monstrosity now, do keep in mind that that compressor and the turbine are physically connected. And so part of the work that is produced by that turbine is being used to drive the compressor. Okay, so I didn't draw that there because I didn't want it to look even more congested than it was, but there you go. All right, so number one, I do note that it is cold air standard. I also note that it is in SI units. Woohoo! So that's fantastic. I also have, unfortunately, I've got some isentropic efficiencies. I've got a regenerator effectiveness of 70%. So yeah, might have a little bit more work cut out for me in figuring out what all those states are, but I think I'm going okay. So let's go ahead and find things. So my back work ratio, it is going to be the work for the turbine, or work for the compressor over the work for the turbine. So it's going to be my work in over my work out. And this is all cold air standard. So I'm applying my first law for an open system to the compressor and the turbine to calculate the work in and the work out. Again, watch the video on at least the Brayton cycle, the simple Brayton cycle, and well, I mean, just watch the videos, right? For calculating or for applying your first law and getting things in terms of delta H's to figure out whether it's H2 minus H1 or H1 minus H2. In this case, it's H2 minus H1. I will say, it's an open system. It's all going to be terms of delta H's, and you can kind of figure out which one's going to come first because you need that work in to be a positive number. Well, the amount of energy associated with that working fluid is going to be higher after put work into it than it is before. So H2 is bigger. With the work out, all right, you're extracting energy, right? And so your H4 is going to be bigger than H5, right? Because your energy associated with that working fluid is going to be higher before you extract energy than after. So it's going to be H4 minus H5. And of course, cold air standard assumptions to the rescue. All I need are those CP values. So this is going to be CP T2 minus T1 over CP 4 minus 5. I think that's good. Of course, my CPs are going to cancel out, so that's fantastic. Now I need my thermal efficiency equation. So I could put it in terms of 1 minus Q in over Q out, or I could put it as work net out over Q in. I'm going to do it in terms of 1 minus Q out over Q in. Now you might think to yourself, well, where does that Q regen come into play? And the answer is, it is not leaving the cycle. It's not coming into the cycle. So it doesn't count as a Q in or Q out. It's just kind of moving heat around within the cycle. So it doesn't come into play in calculating that thermal efficiency. It affects it, but it doesn't go into play with calculating it. So the Q out is going to be between 6 and 1. I know it's going to be in terms of H's. So think about which one's going to be bigger. H6. 6 minus H1, right? Because you're rejecting heat, right? You're going to have more energy associated with the working fluid before you reject the heat than after. And then Q in is between 3 and 4, H4 minus H3. And of course, now this guy can be put into CP delta T's. So CP times T6 minus T1, CP T4 minus T3. And so, of course, those CPs are going to cancel out. So, but I do want to make sure that we kind of, so my governing equation for backwork ratio right there. My governing equation for that thermal efficiency is this guy right here. So on a test, that is exactly the way I'm going to ask it. I'm going to say, part A, give me the governing equations for these things in terms of H values or temperatures, depending on whether you're assuming air standard or cold air standard assumptions. Then I'll give you, and then I'll say, okay, find H1 or T1 or whatever the case may be, right? And that way I can make sure I can give you as much credit as possible. So if you screw up one of those temperatures, it's not going to tank the whole problem. Okay, I want everybody to do well in here, but I also want you to learn the material. So, all right, so T1, I know that. Let's figure out state 2. So state 2. And unfortunately, I do have an isentropic efficiency after that, or for that compressor. So I do need to make sure that I'm going to calculate a 2S. I'm also going to calculate a state 2. So state 2, I'm going to apply my isentropic relationship. Let's go look at those isentropic relationships. So this guy is going to be the one that I use because I know the pressure ratio. The pressure ratio is 8. Perfect. All right. So I've got T2S over T1, 2 over P1 to the K minus 1 over K. All right. So my T2S ends up being 525.32. Okay, but of course that's not the value that I'm going to plug into my equation. I need to use my isentropic efficiency of that compressor to figure out. So yeah, so this is going to be CP T2S minus T1 over CP times T2 minus T1. And so I end up getting a T2 value of 551.5 Kelvin. I will go ahead and kind of highlight that because that's the number that I'm going to plug into my governing equation there. All right, state 3. So state 3. And unfortunately, dang it, I don't know it. And I can't apply an isentropic relationship or anything, so I'm gonna have to come back, I think. Actually, maybe not. Let's think about what we do have. We do have a regenerator effectiveness, so maybe this would be something, right? So I know, and I'm going to go back to the drawing that I had just a couple of pages up because it's the same numbering, but it's super convenient. So you could define that regenerator effectiveness, that Q regen between for the bottom squiggly or the top squiggly. So if we do it for the bottom squiggly between 2 and 3, Q regen is going to be CP times T3 minus T2. But again, the maximum heat that would be transferred into that bottom squiggly would be if that working fluid heated up all the way to T5. So CP times T5 minus T2. So let's go ahead and, oops, not that. There we are. That on here. So this is, oops. This is going to be CP times our diagram, T3 minus T2 over CP max, which would be if that working fluid heated all the way up to T5. Okay, so now got an equation at least, so I know my T3 is going to be my regenerator effectiveness times T5 minus T2 plus T2 equals something. But of course, you'll notice I need T5. So I don't have T5. If you look at your diagram, you don't have him yet. That's okay. I'm on my way. I'm going to get him. Let's get state 5 or state 4. So state 4, I know state 4. I think I do. Yeah. It's just not on my diagram up there. I was kind of lazy, wasn't I? If I look up at the wording, it says the air entering the turbine, T4, is equal to 1370. So that's convenient. Yeah. So 1370, perfect. So state 4, T4 is 1370 Kelvin. I guess I really didn't have to rewrite that, but I'd already started, so I wanted to go ahead and pretend that that was what I was planning to do in the first place. All right. State 5, we're moving right along. And I want you to notice, well, actually, never mind. I guess yeah, I thought maybe I could get away with not calculating T6, but the way I've written my thermal efficiency equation, kind of got to. So that's okay. All right, so state 5. This is after that after that non-isentropic compression, or after that non-isentropic expansion in the turbine. So I will have to get state 5s and a state 5. All right. So isentropic relationship between T4 and T5s. This would be P5 or the K minus 1 over K. All right, so let's see. I know K is 1.4. I know T4. Let's figure out the pressure ratio. All right, again, when you got a heat exchanger, you got piping or anything like that with these cycles, in this class, go ahead and assume you don't have any pressure drops. So, for example, the piping from 2 to 3, no pressure drops. From 3 to 4, no pressure drops. And then, yes, there's a pressure drop from 4 to 5 because it's an expansion process within a turbine, but 5 to 6, nope. And across our imaginary heat exchanger over there, nope. So I know P2 over P1, so that means I know ratio P5 over P4, right? So P5 over P4 would just be 1 over 8. So 1 over 8. So let's see. 756.3. 6 Kelvin. Perfect. Perfect. All right, now T5. So the nice thing about these problems is they're somewhat repetitive. Like there's a lot of repetition in there. So it's a blessing and a curse. um, but yeah, I guess in a 5-week period, you don't have too much time to get sick of it. So it's more of a blessing. All right, so ideally with a turbine, you get a whole bunch of work out of it. So that's going to be, that's going to be on the bottom. So this is going to be CP. It's between T4 and T5. T4 minus T5. CP times T4 minus T5S. And I solve for my T5 and getting 817.7 Kelvin. So definitely need that for my governing equations. And I also need it up here to find T3. I end up getting 737.8 Kelvin. So let's see, do I need anything else? I need T6, unfortunately, but that's okay. Let's go ahead and get him. So state 6, this is after it passes through my regenerator. So I have a regenerator effectiveness, and I'm going to define that regenerator effectiveness using the top squiggly, right? Just like we did up here. Define that regenerator effectiveness with the top squiggly. So in reality, Q regen is CPT5 minus T6, but the maximum Q regen would be if that working fluid cooled off from state 5 all the way down the incoming temperature at state 2, right? So CP times T5 minus T2. All right, so regenerator effectiveness, CP, like having my picture there, CP times T5 minus T6 over CP times T5 minus T2. So I can get my T6. I end up getting 631.5. Oh, I'm sorry. No, it was 3. Started to write 3, and I second guessed myself. Kelvin. Okay. So that's the number that I'm going to plug in. And I end up getting a thermal efficiency of 46% here. And I cannot believe, box, like, I can't really believe that I don't have one for thermal efficiency. Not thermal efficiency, but my back work ratio. That's okay because it really is. It's plug and chug. It's going to be something as well. Right? Some ratio. Okay. Alrighty. So I think that's it. Next thing would be reheating and intercooling. And I guess, yep, that's next on the docket.